So chapter 10 is all about acids, bases, and salts. And this is a fairly long chapter, so I'm going to see if I can get through it in one recording, but you may find that you want to cut it into a couple different segments, and I will try and point out as I go through good places to stop in terms of the content. We'll see if I remember to do that. Hopefully I will. So let's start out with some basic definitions of what's an acid and what's a base. And there's going to be two models that we look at, and the first is the Arrhenius acid-base theory. And Arrhenius is saying that an acid is something that contains hydrogen, that produces H+ ions in solution. For instance, HNO3, you'll notice, has an H written first in the compound formula, and that when you put it in water, it dissociates and makes H ions. So I could look at this formula and see, oh yeah, H, therefore this is an acid according to Arrhenius. An Arrhenius base is something that contains hydroxide, so that it produces hydroxide ions in solution. So example, we have sodium hydroxide. Look, there's the hydroxide in solution, therefore Arrhenius would say this is a base. So let's do some practice of these concepts. If I can make my slide go forward. Next. And look at a variety of types of compounds that you might be faced with. So notice this question says, identify each of the following substances as an Arrhenius acid, base, or neither. And what we're looking at in terms of answering the question is just a formula. So the Arrhenius model works when we're looking at just a single formula. The second model that we're going to look at, Bronsted-Lowry model, works when we're looking at how something behaves in a reaction. So that's a distinguishing factor between the two. Arrhenius, we're looking at a particular formula all by itself. And so we can look at HCl and we can ask ourselves, does it contain hydrogen? Does it contain hydroxide, or does it contain neither? And we see that HCl does contain hydrogen, and the hydrogen is written first, showing us that that is an acidic hydrogen. So HCl indeed is an acid. When we look at CH4, on the other hand, there is hydrogen present in the formula, but it's not written at the beginning of the formula, which tells us that CH4 is actually not an ionic compound. It's a covalent compound, and that hydrogen is acting like a nonmetal. Remember, hydrogen's tricky. It can be a metal, it can be a nonmetal. When it's written first, it's acting like a cation. When it's written second, it's acting like a nonmetal. So in CH4, the hydrogen is not written first in the formula, so therefore this is not an acid. Is there an OH in the formula? No. So this is not a base either. So this is neither. MgOH2, we have a metal paired with hydroxide. So that tells me that we have an ionic compound and that the OH is present as hydroxide with a -1. And so according to Arrhenius, bases contain hydroxide ions. So this is a base. On the last one, we have CH3OH. So it looks like there's an OH present. However, the OH is not paired with a metal. In fact, there are no metals in that compound, which tells us that this is not an ionic compound. It's a covalent compound. And because that's the case, that OH that we're looking at there is not hydroxide. It's actually an alcohol group, which is something different. So because this is not an OH present with a metal in an ionic compound, this is not a base either. So this is neither as well. So like I said, we're going to have two theories of acids, and we just talked about Arrhenius. Let's now go to Bronsted-Lowry. In this case, our acid is a substance that can donate a proton or an H+ ion. Those are the same things. We tend to call H+ ions protons because if you think about it, when the electron goes, the only thing that's left for hydrogen is a proton. So a Bronsted-Lowry acid is a substance that donates a proton to some other substance. It's called a proton donor. A base is a substance that accepts a proton or a hydrogen ion from some other substance, and it is a proton acceptor. So Bronsted-Lowry acid donates protons, bases accept protons. So notice that here we're talking about something actually happening. We're not just looking at a formula and deciding whether something's an acid or a base. And in fact, in order to decide whether something is an acid or a base using the Bronsted-Lowry theory, we need a chemical reaction because we need to see who's donating H's and who's accepting H's. And when we look at this reaction here, we see that the HCl has H's. But what's important here is to notice that over on the other side, my pen's not working, the Cl now doesn't have an H, which means that HCl lost its H. So HCl loses H+. And we know that by looking at the products at what HCl becomes. It becomes Cl-, has no H+. That tells me that HCl is the acid. It lost the H. H2O, on the other hand, becomes H3O+ in the products. So now it has an additional hydrogen ion that was added to it. Because H2O is neutral and I'm adding a proton, now my charge on my water is now H3O+ because of that positive charge. So water goes from H2O to H3O, an increase of hydrogens, so therefore it is the base acceptor, excuse me, it is the proton acceptor, and therefore it's the base. Let's go ahead and, I think, do some examples. No, not yet. So acids in water all pretty much do the same kind of basic activity. They give up their hydrogens. How much they give up their hydrogens depends on whether it's a strong acid or a weak acid, and we'll talk more about that. But we can write what's called a dissociation reaction for acids in water, and this is the basic format. My acid reacting with water, the acid obviously behaves like an acid and donates a proton to water, thus creating an anion of what the acid was made out of. So in terms of Bronsted-Lowry, now we can look at both things that are the acid-base reactivity that's happening in the reactants and what's going on over here in the products. If you think about it, we can look in the reverse reaction, and see what happens. So H3O+ becomes H2O. It has lost a hydrogen. It has gone from H3 to H2. A-, on the other hand, has become HA. It's picked up an H. So on the product side, H3O+ is our conjugate acid, and A- is our conjugate base. And this will always be the setup. Acids and bases on the reactant side, conjugate acids and conjugate bases on the product side. The other thing to notice here is that your acid will always become your conjugate base, and your base will always become your conjugate acid. Okay, let's do some practice. So we want to identify the acid, the base, the conjugate acid, and the conjugate base in each of the following reactions. And I think I have, yes, I have 2 of them here. So go ahead and hit pause on the presentation, and when you've figured out which of these is which thing, go ahead and start it back up. So when I'm looking at this, I'm evaluating if I want to decide whether HCN is an acid or not. I'm evaluating what does it become. So I see that HCN becomes CN-. Notice that's a loss of an H. So therefore, HCN is my acid, which doesn't show up super well, but that's the acid. So I'll write it down here. HCO3-1, if we look at it, becomes H2CO3. So I've gone from 1 H to 2 H's, which means that HCO3-1 gained an H+. Therefore, HCO3-1 is the base. In the reverse direction, CN- goes to HCN. It is gaining a hydrogen, so therefore it is my conjugate base. It is the acceptor. And H2CO3 is becoming HCO3-1, Notice the change in charge because you're losing a positive from something that's neutral. And so therefore H2CO3 is my conjugate acid. On this next one, H2O becomes H3O+. So it is gaining a hydrogen, which tells me that H2O must be my base. H2SO4 becomes HSO4-1, which is a loss of a hydrogen, so therefore H2SO4 is my acid. And then if I look in reverse, HSO4-1 goes to H2SO4, clearly the result of adding a hydrogen ion. So this is my conjugate base, which means that H3O+ must be my conjugate acid. We have substances that are amphiprotic. And what this means is that it's a substance that can either lose or accept a proton, and therefore can either function as a Bronsted-Lowry acid or a Bronsted-Lowry base. For example, H2O. H2O can either gain a proton and become H3O+, or it can lose a proton and become OH-. So water, this is a very classic amphiprotic substance, can either be an acid or a base, depending on what it's reacting with. Acids are classified according to the number of hydrogen ions that they have. So a monoprotic acid is telling you have one hydrogen. So one proton per molecule during an acid-base reaction. Diprotic is telling you that you have 2 protons per molecule, and we can see that shown here in the formula with a 2 on my acidic hydrogens. That means actually I have 2 reactions going on. I have one reaction for the removal of the first proton, which is here, and then an additional reaction that's occurring for the removal of the second proton. Triprotic acids, we're looking at 3 protons. So there's my 3 in my formula. And now I have 3 different reactions to look at because I'm removing 3 different protons. So here's the removal of the first proton, and then I take the product of that reaction and remove the second proton, and then I take the product of that reaction and remove the third. So basically, I start out here with lots of protons, and I end up here having stripped them all away. Polyprotic acid is just a more generic term saying that you have 2 or more protons. So it's going to encompass both diprotic and triprotic acids. Let's talk about how we know whether acids are strong or weak. Strong acids completely dissociate in water. That means they completely throw away their hydrogen. They completely separate, 100%. That means that the equilibrium, if we think back to chapter 9, our equilibrium constant lies far to the right, way far, really favors products. There are essentially no reactants left. So commonly encountered strong acids, and yes, you do need to memorize these because you need to be aware of what they are so that you can easily identify them on a test without having to look them up. And there's some other information that comes with this. So there's 7 of them. Just make up some flashcards. You need to be able to recognize essentially the formulas. You don't actually have to know the names, but if I say is HCl a strong acid or not, you need to be able to tell me, oh yeah, it is, because I memorized that. Weak acids, on the other hand, don't give up all of their protons. In fact, they only give up very few of them. And what that means then is that reactants, in terms of the equilibrium, are heavily favored. So weak acids tend to stay together, so their hydrogen ion tends to stay on the anion, and so you favor reactants heavily. In terms of species present, we can look at this figure. On the left here, we have strong acids. When you put them into water, you completely transfer the proton to water, which makes H3O+. And so I have equal amounts of concentration of products, and over time, obviously, the HA concentration would go to 0 here. On the other hand, with a weak acid, over time, I still have lots of weak acid, and I have very little H3O plus and very little A minus, because the HA just simply doesn't give up the proton very much. That's the definition of a weak acid. Bases, strong bases can be found in hydroxides of group 1A and 2A. So notice it's all of the group 1A hydroxides and the heavy group 2A hydroxides. So when you look at the periodic table, it's all of that first column minus hydrogen, obviously, well, and francium, minus the first and last rows. And then starting at row number 4, going down to row number 6, calcium, strontium, and bromine. So whenever you see these metals paired with hydroxides, those are strong bases, which means everybody else is a weak base, which is nice. Same goes for strong acids. Those strong acids that you memorize, oh, and by the way, you need to memorize the strong bases as well. What's handy about knowing those is that then everything else is weak. So acid ionization constants are essentially the equilibrium constant for the weak acid reaction with water. So we've talked about this dissociation reaction that acids do in water, where I have HA, it's added to water, and it splits up. I can write an equilibrium constant expression for that. Notice here, recalling from chapter 9, I'm only including aqueous and gases in my equilibrium constant expression. So water, which is a pure liquid, doesn't show up there. And again, it's products divided by reactants, concentration given in terms of molarity. That's what those brackets tell you. So that size of Ka is going to be related to the strength of the acid, right? Because if I have a weak acid, then I don't form very, very many products, which means that my product concentration is very small, and my reactant concentration is very large, which means Ka is a pretty small number. So as the percent ionization increases, my strength, obviously, of my acid is going to go up, and as that happens, Ka will go up as well. For bases, let me go back there for one sec here, and just make sure that you're aware. So large Kas go with strong acids, and small Kas go with weak acids. Base ionization constant, similar idea, except now you're reacting a weak base with water. And remember, bases are going to be proton acceptors. So my base, generic B here, is picking up a hydrogen from the water, and in the process is forming hydroxide ion, which is really where the base is at. I can write an equilibrium constant expression for this reaction as well. Similar idea to that with the acids, concentration of my products divided by concentration of reactants. Again, same idea. Strong bases, lots of ionization, which means product concentration will be high, which means Kb will be large. Weak bases, really low dissociation, so reactant concentration is high and product concentration is close to 0, which means that Kb will be really small. So strong bases give me large Kbs. Weak bases give me small Kbs. Salts. These are simply ionic compounds that are soluble in water. So a lot of this will sound pretty familiar because we've already learned about ionic compounds and we've already learned about how they dissolve. So soluble salts completely dissociate into ions into solution. They're simply just an ionic compound is what you remember. Acids and bases, when they get together, perform what's called a neutralization reaction. And what forms is a salt and water. So that's the same as saying an ionic compound and water. So HCl reacting with sodium hydroxide. Here's my acid. Here's my base. So neutralization, by definition, is an acid plus a base. I am forming a salt plus water. Now notice here, let's go ahead and look at this one and then I'll talk about that. H2SO4, again an acid, KOH, again a base. I'm forming a salt, K2SO4, and water. What's great about neutralization reactions is that they are simply double replacement reactions. So in Chapter 9, when we learned about double replacement and the fact that it's simply the metals swapping places, we can see here sodium and hydrogen swap places. So sodium pairs up with chlorine, which is what we see here, and hydrogen pairs up with hydroxide, because water is essentially HOH, a hydrogen ion plus hydroxide. Commonly written, obviously, H2O. Same deal down here with the H2SO4. My metals are going to swap places, so my hydrogen and my potassium swap, which means now the potassium is paired up with sulfate, which is what I see here, and my hydroxide is paired up with hydrogen. Notice it's the same, it would be the same process that we used for coming up with double replacement products. We would look at our raw materials of the different ions and then pair them with their new ion, determine the new formula, and then go and balance the reaction. Water, when it's all by itself, oh, by the way, if you're not feeling comfortable with double replacement reactions, I'd recommend going back to that section, that video on Chapter 9, and watching that again to review. And then maybe testing yourself to make sure that you can produce those same products that we just talked about in that previous slide. So, self-ionization of water. Water, when it's by itself, does a reaction, oddly enough. And what they do is form what are called hydronium ions and hydroxide ions. So essentially, two water molecules get together and pass protons. Overall, because this is water reacting water with water, every time it happens, you produce equal amounts of hydronium ions and equal amounts of hydroxide ions. And here's a nice little picture showing you how that happens. Pretty much that's your oxygen, lone pair of electrons plucking off a hydrogen from another water, and therefore making the hydronium ion and the hydroxide ion. We can write an equilibrium constant expression for this reaction. In this case, both of our reactants were pure liquids, so we don't have anything in the denominator of the fraction. Because this is a specific equilibrium constant expression for the self-ionization of water, it's called Kw, so equilibrium constant expression for water. And they've measured it, and it's equal to 1.00 times 10 to the negative 14th. Great thing about this is you can use it for any kind of solution as long as it's something dissolved in water. Because what we know is, if that's the case, then the product of the H3O plus and the hydroxide ion must always equal 1.00 times 10 to the negative 14th. If you check your blue sheet, you'll see that this is one of the one of the math formulas that you need to memorize. So if you think about hydroxide ion and hydronium ion in water, they're kind of this teeter-totter. So in a neutral solution, they're equal. My hydroxide, which is this first picture here. My hydroxide ion in blue and my hydronium ion in blue, they're equal. But if I add lots of acid, like is shown in this second picture here, my concentration of hydronium ion is going up, but at the same time, if that happens, my hydroxide ion concentration has to go down. Now, it's a little misleading when you look at the scale here that up for acid, an increase in concentration is actually moving down the scale, because those are getting to be actually larger numbers. The opposite is true if I add hydroxide. If I add hydroxide, then the hydroxide ion concentration rises and the hydronium ion concentration decreases. So there's three possible situations that we want to be able to make sure that we understand here. One, hydronium ion concentration could equal hydroxide ion concentration, in which case the two, my acid and my base concentrations are equal, and that's a neutral solution. My hydronium ion concentration, which is essentially my acid in water, is greater than the hydroxide ion concentration. Therefore, that is an acidic solution. If, on the other hand, my hydroxide ion concentration is larger than my hydronium ion concentration, that's a basic solution. So let's go ahead and do some work with this formula that we have. So keep in mind here we're working with the idea that Kw, which equals 1.0 times 10 to the negative 14th, is equal to the concentration of hydroxide ion times the concentration of hydronium ion. And remember, I can use this for any solution as long as it's aqueous. So the question says, calculate hydronium ion or hydroxide ion as required for each of the following solutions at 24 degrees Celsius and state whether the solution is neutral, acidic, or basic. So in A, I've been given the concentration of hydroxide ion, so I'm going to put that into my formula and solve for my hydronium ion concentration. So I have 1.0 times 10 to the negative 14th equals hydroxide ion concentration, which is 1.0 times 10 to the negative 4th, and then hydronium ion concentration, which I'm trying to solve for. So I need to divide both sides by 1.0 times 10 to the negative 4th, excuse me, and that will give me my hydronium ion concentration. So H3O plus, you can do that math on paper separately. So 1.0 times 10 to the negative 14th, and I want to divide that by 1.0 times 10 to the negative 4th. You should have your calculator out for this, although this one you actually could do in your head. And that gives me 1.0 times 10 to the negative 10th molar for hydronium ion. So if we think about that, my concentration of hydroxide ion is 1.0 times 10 to the negative 4th. My concentration of acid in the form of hydronium ion is only 1.0 times 10 to the negative 10th. That tells you you've got way more base than you do acid. Therefore, in solution A, this is basic. In solution B, I have 2.0 molar H3O plus. So that means we're solving for the hydroxide ion. So 1.0 times 10 to the negative 14th, here's my base equation here. Hydroxide ion concentration, which I don't know, and 2.0 molar. So solve for hydroxide by dissolving both sides, by dividing both sides by 2. So 1.0 times 10 to the negative 14th divided by 2 is going to be 5 times 10 to the negative 15th. Leave my hydroxide ion concentration. Oops, forgot my units. That'd be molarity. So again, evaluating, do I have more hydronium ion concentration? Do I have more hydroxide ion concentration? Well, pretty clearly I have way more acid. So therefore, this solution is acidic. We can talk about the acidity and basicity of a solution using something called pH. And the reason we use pH rather than talking about hydronium ion concentrations all the time is that pH is kind of simplified. The number is a little bit easier to understand because it's based on a log-based scale. And so we don't have to say things like 1.0 times 10 to the negative 14th. We can just say 1. So it's compact. We know that pH decreases as H plus increases. So acidic pHs are going to be, oops, let me go back. Or see, whoops, go back. pHs are going to range between 0 and 14, and we can break that up into 0 to 7 and 7 to 14, where 7 is neutral, right? Exactly in the middle. But 0 to 7, you have an acidic solution, an acid. 7 to 14, you have a basic solution. So let's go ahead and calculate the pH for each of the following solutions. Oh, and just a heads up, that equation for pH is, again, one that you want to memorize. That pH equals the negative log of the hydronium ion concentration. Now remember, hydronium ion is the same as saying H plus, aqueous. So you can write either of those terms, depending on what you feel more comfortable with. Now for some reason, this is cut off part of my deal here. So this should actually be in A, it should be 1.0 times 10 to the negative 4th molar H3O plus. There should be a plus out there. And we want to calculate pH, which means I need hydronium ion concentration, which I do have here in A. So my pH will be equal to the negative log of 1.0 times 10 to the negative 4th molar. So whip out your calculator to take the negative log, 1.0 times 10 to the negative 14th. Whoops, not negative 14th, negative 4th. Negative log 1.0 times 10 to the negative 4th, which is, my calculator is not working. Should be 4. Hopefully that's what you're getting. We'll try a different calculator. Log 1.0 times 10 to the negative 4th. Yeah, it's 4. Phew. It's like the world stopped turning when your calculator doesn't work. Okay, in B, I'm given 0.040 molar hydroxide ion. Now notice, in order to calculate pH, I have to have hydronium ion. So I cannot take this 0.040 and just pop it into the pH equation. I've got to do something else first. I have to calculate my hydronium ion concentration. So if you think back, we have this handy equation that relates hydronium ion concentration to hydroxide ion concentration. It was 1.0 times 10 to the negative 14th equals OH minus concentration times H3O plus concentration. So I can take this value and plug it in here and solve for my hydronium ion concentration. So let's go ahead and do that. So that's essentially going to be 1.0 times 10 to the negative 14th divided by 0.04, which gives me a hydronium ion concentration of 2.5 times 10 to the negative 13th molar. Now I can put that into my pH equation. So the pH equals the negative log of 2.5 times 10 to the negative 13th. So take the negative log, and I get 12.6. Hopefully you did too. Significant figures on pH. Mr. Stoker, the author of your textbook, will go into the rules of that. I'm not going to hold you accountable to them. So pHs are generally either reported as whole numbers or to the tenths. So it's pretty safe to report to the tenths in terms of significant figures for this class. All right, let's do some more. So now, this question comes at it from the opposite side. Instead of giving you the hydronium ion concentration and asking you to find the pH, it's giving you the pH and asking you to find the hydronium ion concentration. And what's important to recognize here is that that equation, pH equals negative log of the hydronium ion concentration, can be solved for the hydronium ion concentration. And if you remember your algebra skills and how to work with logs, you'll know that 10 to the negative pH is equal to the hydronium ion concentration. If you remember your math and you know how I did that, fantastic. If it looks like totally out in left field for you, I would recommend just simply memorizing this equation in addition to this one. So either you can derive the second equation if you know how to work with logs, or not, depending. So if the pH of the solution is 5.85 and I want the hydronium ion concentration, I'm going to say 10 to the negative 5.85, oops, which I do actually need to put into my calculator. You can't just report it like that as your answer. And that gives me 1.41 times 10 to the negative 6 molar. And we could also ask at this point, and actually we could have asked when we knew the pH, is this solution acidic, basic, or neutral? What do you think? Well, given that the pH is less than 7, and we know that pHs of 0 to 7 are acidic, this is an acidic solution. Which is what my next slide is all about, even though I've just covered it. Yes. So the higher the pH is, the more basic you are. If you're less than 7, you're acidic. The lower your pH is, the more acidic you are, which we've been talking about, but here's a slide just in case. And then just a general picture of as you increase your concentration of hydronium ion, you're becoming more acidic, and your hydroxide ion concentration is decreasing. When they're equal, they're neutral, which that's kind of a handy number to know, 10 to the negative 7th. And then at the other end, as you decrease your hydronium ion concentration and increase your hydroxide ion concentration, you get more basic. So if you were thinking, hey, now might be a good time to pause and go do something else for a while and let my brain rest for chemistry, then this would be a good idea. So pKa's are going to give us some directions about how strong an acid is as well. And the pKa, kind of like pH, that whole P thing, just means we're going to a log base. So a pKa is equal to the negative log of the Ka. And remember, Ka is our acid dissociation equilibrium constant. So it's calculated exactly the same way you calculate pH from H3O+. And what it tells you, and let's just run through a calculation here. So if in this question it says calculate the pKa for HF, given that the Ka for this acid is 6.8 times 10 to the negative 4th. So we know that pKa equals the negative log of the Ka. So we have negative log of 6.8 times 10 to the negative 4th. Which gives me 8 point, oops, hold on. I forgot my parentheses. Negative log 6.8 times 10 to the negative 4th gives me 3.16 or 3.17. So just like pH, it's an easier way of expressing acid strength. So, whoops, let's go back there. I had one more thing I wanted to say. So as your Ka gets larger, let me just check this before I say this. So if we had a Ka of, let's say, 9.8, of 6.8 times 10 to the negative 6, so I'd have negative log 6.8 times 10 to the negative 6th. Okay, so as my Ka gets larger, as my Ka gets smaller, my pKa will get larger. So large Kas gives me small pKas, and small Kas give me large pKas. So let's back up a second and see what that actually means. If I have a large Ka, remember that went with a strong acid. So that means a small pKa will go with a strong acid, and a large pKa will go with a weak acid. Buffers are pretty amazing. This is an aqueous solution that contains a substance that prevents major changes in solution pH when small amounts of acid or base are added to it. And the reason I say this is so amazing is if you think about it, when you got up this morning, maybe you drank some coffee, or maybe you had some orange juice, or maybe throughout the day you had some Coke or something. All those things have different pHs. So coffee is actually pretty basic, whereas orange juice and soda, pop like Coke or any of those kind of energy drinks are pretty acidic. And in fact, if you look at the back of a Coke can or a Pepsi can, it will list phosphoric acid as one of the main ingredients, which apparently it's there to give it nice flavor. But regardless, your blood pH can only exist within a pretty narrow range, 7.35 to 7.45. And if you go outside of that range, you can either go into acidosis, meaning your blood is too acidic, or alkalosis, meaning your blood is too basic. And that causes a whole host of problems to your system. So it's pretty amazing how balanced we are in the sense that you can drink essentially acid in the form of Coke. Coca-Cola there, or base in the form of coffee, and yet your system, your blood pH doesn't vary very much. So what's in your blood that's helping out there, you're putting in all these different acids and bases, and your blood has a buffer that's dealing with the fact that you're putting in these acids or bases, and it's protecting your blood pH so that your blood pH doesn't stray outside of that pretty narrow range, even though you're drinking lemonade. So what are buffers? They are weak acids or bases that contain their it's a weak acid and its conjugate base, or a weak base and its conjugate acid. And when it says here containing a common ion, it's referring to that conjugate part. So typically it's a weak acid and its conjugate base, or like I said, a weak base and its conjugate acid. They've got two active chemical species. So one substance to react with and remove added base, that would be whatever is your acid part of the buffer, and one part to react with and remove added acid. And that part of the buffer is going to be your base, right? Acids and bases react together. So if I had some buffer, like for instance, the buffer in this case would actually be A and A minus. So my buffer would be the weak acid, HA. Hydrogen is kind of important to include there. My weak acid HA and its conjugate base A minus. So notice the relationship between weak acid and its conjugate, or really acid and its conjugate base anywhere, is that we've removed a hydrogen. So if I have HA A minus as my buffer, we can write this reaction showing, and I can't draw, showing the buffer system, which is essentially putting your acid into water and showing what it would produce. So if I add hydroxide ion to this buffer, it's going to react with the hydronium ion, or it's going to react with the HA and produce water, which will neutralize it. So my buffer is pretty amazing in that I can add hydroxide, I can add strong base to it, and the buffer turns my strong base into water, which is neutral. That causes some stress on the system because my H3O plus is being consumed in the neutralization. And if you'll recall from our conversation of equilibrium and Le Chatelier's principle, when I'm removing my products, my equilibrium will shift around to readjust. So my equilibrium in this case will shift to the right to produce more hydronium ion, which will then raise my pH up again to keep it close to its original level. So even though I've added base, it's been turned into water, and then in addition, my equilibrium system of my buffer has shifted around to compensate for that change in concentration and has produced a little bit more acid to offset that base as well. On the other hand, if I'm going to add acid to a buffer, there's my buffer reaction again. In this case, my hydronium ion concentration is coming in, and it's going to increase the amount of hydronium ion present, total. It's too much for the poor little hydronium ion, and so my equilibrium is going to shift back towards reactants. And since that's the case, acid will get consumed, and therefore the pH will drop back down to where it was originally. So let's look at some examples out of your textbook. Number 82 in Chapter 10. Number 82 says, predict whether each of the following pairs of substances could function as a buffer system in aqueous solution. So keep in mind, what's a buffer? A buffer is a weak acid and its conjugate base, or a weak base and its conjugate acid. And what's important here is to recognize that if I have a weak acid and its conjugate, that conjugate is actually going to be appearing as part of an ionic compound. So for instance, in 82A, we have HNO3 and HCl. Well, first off, I've memorized my strong acids and bases, and I know that neither of those are weak. So automatically, that's not going to be a buffer. I need a weak acid and its conjugate, or a weak base and its conjugate. So two strong acids, not a buffer. In B, I have HNO2 and KNO2. And if we look back at our strong acid table, in case you haven't memorized yours, you'll see that HNO2 is not a strong acid. So therefore, when I'm looking at this, now I've got a possibility. I've got HNO2, that's a weak acid, and we have to think for a moment, what is the conjugate of HNO2? What's the conjugate base? Well, it's HNO2 minus a hydrogen, which means that I'm looking for a source of the nitrite ion. Now the second thing that's listed there in B is KNO2, which, if you think about it, is an ionic compound where the potassium is just acting as a carrier for the nitrite ion. So HNO2 and KNO2 provide all the parts of a buffer, a weak acid and its conjugate base. So that could serve as a buffer. In C, I've got sodium acetate and potassium acetate. I don't have any acids there. I just have salts. So that can't function as a buffer either, because even if I had a weak base, I'd need a conjugate acid to go with it. In D, I have acetic acid and sodium nitrate. So that's not going to function as a buffer either. I do have a weak acid in the acetic acid, but I don't have a source of its conjugate, right? The conjugate base of acetic acid is the acetate ion, and sodium nitrate isn't going to give that to me. So the only one of these that could act as a buffer system was B. Let's look at number 86 as well. 86 says, write an equation for each of the following buffering actions. The response of an HPO4 negative 2 minus phosphate ion buffer to the addition of hydroxide ions. So what this is asking for is, first, what is my buffer? And it tells me it's HPO4 negative 2. And the other part of my buffer is PO4 negative 3. So when we look at this, we can see I have a very weak acid here and its conjugate base. So definitely a buffer. And then I'm adding hydroxide ion to this. So the way to think about answering this problem is, I'm adding hydroxide ion. What is present in the buffer for it to react with? Well, it's not going to react with phosphate ion because this is two anions, first of all. Over here, however, although I have an anion, I also have the source of an H. This is my acid, HPO4 negative 2. So hydroxide ion will come in and react with the acid. And so what we're essentially writing here is an acid-base reaction, where we know from our Bronsted-Lowry discussion that my acid is going to lose its proton and my base is going to pick it up. And because I know that, I can say, okay, HPO4 negative 2 is going to lose the proton, so it will become phosphate, which handily, guess what, is the other part of my buffer. That's good news. And what's the other thing I'm going to form? Oh yeah, H2O, hydroxide plus hydrogen ion. So here I've taken hydroxide, I've turned it into water. I've consumed some of my acid in my buffer, but I've also produced some of my base. So in terms of that equilibrium expression, reaction for the buffer system, I've done two things that Le Chatelier's principle tells me what will happen with. I've both increased the concentration of my product while decreasing the concentration of my reactant. And both of those tell me that equilibrium will shift towards my reactants, thus increasing the concentration of my acid in solution, bringing it back to the pH that I started with. Pretty amazing what buffers do. Electrolytes. These are essentially looking at characteristics of different substances that when we put them in water, do they dissociate or don't they dissociate? If they do, they're dissociating into ions, and those ions are producing solutions that conduct electricity. Turns out that acids, bases, and soluble salts, when we put those into solution, they all produce some level of ions. And so we can categorize them as electrolytes, a substance whose aqueous solution conducts electricity. There's three types. There's non-electrolytes, things that we put into solution, they dissolve, but they don't conduct electricity. And these are classified as covalent compounds, right? Because covalent compounds don't have ions. So sugar, for example, we know dissolves super well in water, it's not an ionic compound. So when we dissolve it, it stays as a molecule of sugar. It's a covalent compound. It doesn't form any ions, therefore it's a non-electrolyte. So what they're showing you here in this picture is they've made a solution of sugar, they've got some electrodes in it, and then the light bulb is supposed to be lighting up. And clearly it's not, because there's no conductivity here, because you have no ions. We also have strong electrolytes, which are strong acids, strong bases, and soluble ionic compounds, or soluble salts, which if we make a solution of, we know that strong acids and strong bases completely dissociate, and we know that soluble ionic compounds completely dissociate. So lots of ion concentration, lots of conductivity, and so when you make your solution this time and hook it up to the light bulb, voila, the light bulb lights. So those are strong electrolytes. Strong acids, strong bases, and soluble ionic compounds. We also have weak electrolytes. These are weak acids and weak bases. And the reason these are called weak electrolytes is because they do dissociate somewhat, which we know weak acids and bases do, but not a lot. We know that weak acids and bases prefer actually to stay together. So there is some ionization, some dissociation, but not a whole heck of a lot. So when you make the solution, your light bulb lights up a little bit because there is some conductivity, but these are classified then as weak electrolytes. In addition to weak acids and bases, weak electrolytes also include insoluble ionic compounds, because if you'll recall, insoluble ionic compounds actually do dissolve just a little bit, making them a weak electrolyte. When you react acids and bases together, it can be very useful to use this reaction in order to be able to figure out concentrations of unknown solutions. And this actually is something that you'll do quite a lot in the health field of titrating something against something else. So blood titrations to figure out a variety of things, urine titrations, all kinds of titrations that you're doing. You may or may not actually be doing a titration like we'll do in lab, but the fundamental idea is pretty much the same. So an acid-base titration is a neutralization reaction in which you have a volume of an acid or a base with a known concentration. You completely react it with a measured volume of a base or an acid with an unknown concentration for the purpose of determining what that unknown concentration is. For a strong acid and base reaction, we know that these are neutralization reactions. So it pretty much always comes down to the H's reacting with the OH's to make H2O. Your setup, which you can see here, you have this thing called a burette, which is a long piece of glass tubing that has graduated markings on it to tell you the different volumes. And then you have your unknown substance being titrated, which you know the volume of, but you don't know the concentration. And then you're essentially adding your known concentration until you see a color change. So in order to see a color change in a titration, you have to use what's called an indicator, which is just something that changes color when the reaction is finished. You choose them carefully to make sure that they actually correlate to the pH range that you're doing the reaction at. Not something we're going to talk too much about in terms of Chemistry 121, but good to just be aware of that if I have two colorless solutions and I put them together, how do I know when the reaction's done? Well, I don't, unless I put something else in there that changes color for me when the pH changes. So you can see here, there's an indicator that's yellow in acidic solution, but after you've added sufficient amount of base, then actually most indicators are incredibly sensitive, so one drop turns your solution basic would change the color from yellow to red. To solve titration problems, there's a couple different steps that can help you here. So I'm going to run through the steps and then we're going to run through an example. So first step, whenever you're faced with an acid-base titration problem, is to write out and balance the chemical reaction. The second step is to use the reactant that has both the molarity and the volume provided to calculate the number of moles of that particular thing. Step 3, take those moles that you obtained in step 2 and change them to moles of the reactant that you don't know the concentration of or you don't know the volume of. Whatever the question's asking you about, whichever reactant that is, that's what you want to change moles to. It's very similar to what we did in Chapter 6. where you know moles of one amount and you need to get to moles of something else. And you can do that, obviously, using the balanced chemical reaction coefficients. Step 4, take those moles now of the substance that you wanted and change them to the requested unit. So that might be molarity, it might be a volume unit, depends on what the question's asking. So let's go ahead and do an example. You have 35.0 milliliters of 0.50 barium hydroxide, and it's used to titrate. There's that key word there, titrate. Titrate there is just telling you these two things are reacting together in a neutralization reaction. So is used to titrate 100.0 milliliters of HCl. What is the concentration of HCl? So step 1 is write out and balance the reaction. So barium hydroxide plus HCl. And remembering that neutralization reactions are simply double replacement reactions, I know that my metals are going to swap places, so barium and hydrogen are going to swap. So I'll be working with barium, which has a +2 charge, with chloride, which has a -1 charge. So I will have a formula of BaCl2, 2, get rid of that 3, 2, plus HOH, which is essentially the same as H2O. The reason I've written it as HOH is sometimes that can be easier to balance in the sense that I can balance hydroxides and hydrogens rather than balancing hydrogens and oxygens. So now I can look at this and see, well, on the reactant side I have 2 hydroxides. On the product side I have 2 chlorines. So I'm going to put a 2 in front of my HCl. That means now I have 2 hydrogens and 2 hydroxides, which means putting a 2 in front of my HOH will balance the reaction. So there's step 1. I balanced the reaction. Step 2 was to take my volume and molarity of the substance that it was given and use it to calculate moles. So when I go back and read the problem, I see I have 35 milliliters and a molarity for barium hydroxide. So remember, with molarity, we can use it as a unit conversion, just like we did in Chapter 8. And if you don't remember how to do that, I recommend you go back and bone up on that, or brush up on that, sorry, before you do this problem. So 35.0 milliliters barium hydroxide is where I'm started. And my first step is to change that to moles using molarity. So 0.50 moles of barium hydroxide is equal to 1 liter of solution, which is what I have there. So this is that unit conversion that I got from my molarity. So milliliters, whoops, hold on, milliliters don't cancel. What did I forget to do? Shoot, I forgot to change from milliliters to liters. So I'm going to tack this on down here, 1,000 milliliters and 1 liter. Now I can get rid of milliliters, and I can get rid of liters. And right now I'm in moles of barium hydroxide. So this was step 2, get to moles of the substance that I have volume and molarity for. Step 3 was to change from moles of that substance to moles of the substance that I need to know about. So in this question, I need to know the concentration of HCl. So that means I need to know the moles of HCl. When I look at my balanced chemical reaction, I see that there's 2 moles of HCl for every 1 mole of barium hydroxide. So 1 mole of barium hydroxide goes on the bottom, and 2 moles of HCl goes on the top. So now moles of barium hydroxide cross out, and I'm in moles of HCl. Step 4 was to solve for whatever it asked me for. So the question says, what is the concentration of HCl? Which is really saying, what is the molarity of HCl? Molarity, remember, is in units of moles per liter. I have a volume of HCl. It's 100.0 milliliters. So right now, I'm in moles of HCl. I need to have moles per liters. So I'm going to divide by my volume of HCl changed to liters, which is 0.1. So now I have units of moles over liters, which is molarity. And at that point, I can stick the whole thing into my calculator. So 35 times 0.5 divided by 1,000 times 2 divided by 0.1. Oops, 0.1. I get 0.35 molar. For my HCl. Okay, so those titration problems, there's a couple different examples of them. They're pretty similar to what we just did. I highly recommend looking at 111 and 112 for more examples of those if you're looking for that. Homework in general, you're looking at 1 through 38, 41 through 86, 93 through 100, and like I mentioned, 111 and 112. We pretty much covered the entire chapter in Chapter 10, except for the section on the Henderson-Hasselbalch equation, which is section 10.13. So we're skipping those problems, and you can skip that in your reading. But you're responsible for everything else.